Okay, hello everybody. How was lunch? Awesome. Okay, all right. Thanks very much for coming. My name is Josh Bongard. You can call me Josh, that's fine. I am a roboticist, so we're going to spend the next 45 minutes talking about robots. I'm going to talk a little bit, but I'm going to also show you some videos of some cool state-of-the-art robots that you may have seen before, like this robot. Have you seen this robot? Okay. I'll show you some of those kinds of robots. I'm going to show you some robots that we've developed here in my lab. So I'm a professor here at the University of Vermont. And if you happen to come here as an undergraduate, you might take my class, CS206, Evolutionary Robotics, where you actually get to evolve your own robots. I spend half my time here at UVM teaching classes on evolutionary robotics, and the other half of the time I spend in the lab with my grad students building robots and trying to use those robots to answer questions about things like evolution, language, and the thing that's in here. And we're going to talk about that today. So we got 45 minutes. I'm going to start with robots. You're all budding engineers, right? So we'll talk a little bit about the nuts and bolts of robots to start with. Then we'll talk about evolution, language, and then we'll end with the mind. Sound good? Okay. Please feel free to ask any questions. If you have any, just put up your hand and we'll make this as interactive as possible. Okay, so let's start with some other people's robots. Who's seen this robot before? This is the Big Dog robot from a few years ago. Big Dog is carrying 325 pounds on its back. I, first of all, wouldn't be carrying 325 pounds on my back, but I certainly wouldn't want to be doing that when I go out over the ice here on campus in January, right? Pretty amazing machine, built back in 2005. Now we're starting to live in the era of drones. This is a video from one of my colleagues, Professor D'Andrea, who's resting a glass of water on the drone in the center. He's now controlling it with a wireless joystick. The drone does not drop a bit of water. Now he's playing catch. Notice the human dropped the ball, not the robot. So one of these days we'll be able to play catch with our drone. This is actually a TED video, so if you Google D'Andrea TED, you can go and watch the rest of this video. It's super, super cool. He is a professor at ETH in Switzerland, in Europe. Yeah. So that's quadcopters or drones back in 2013. Here's a 3D biped, if you watch carefully. Everybody see that? Watch carefully if you missed it. Pretty amazing, huh? So this is a 3D biped that was built at MIT by Marc Raibert. Marc went on to found Boston Dynamics, which is the company that produced Big Dog. I've left the date of this video off this slide. So have some of you heard this talk before? No? Okay. Anybody want to take a guess? When was this video shot? 2007. 2007? Other guesses? 2000? Keep going. 1992. So what is that? Over 25 years ago, right? So obviously robots are super cool. There's some pretty cool ones out there, but there have been pretty impressive robots out there for 25 years. Where are they? Right? Why aren't there robots shoveling the snow or cutting the grass or putting the dishes in our dishwashers? Do you have an idea? We don't have AI to go along with them, right? So we know how to build pretty sophisticated machines. Here's some more sophisticated machines. These are industrial robots up here in the top right. And industrial robots over the last 100 years have completely changed the way that we build things indoors. Yeah? So Henry Ford, who helped to invent the automobile, also invented the factory, came up with this idea of mass production. So you create this thing called a factory, and in the factory you have a whole bunch of wooden tables, and you have something that's being built, and you have these people, and each person is a specialist. They don't build the entire motorcycle, they add one piece to the motorcycle, and then they move to the next table, and they add the same piece to that motorcycle, and on they go. That's mass production. That was replaced in the 1960s and 70s, or the people were replaced in the 1960s and 70s by machines, which now automate the way that we build things indoors. Instead of people doing one very specific task over and over again, we now have industrial robots that do the same task over and over again. Industrial robots now allow our civilization to build lots and lots of stuff very, very cost effectively. We paid a cost as a society for doing that, which is we put these people out of work. Now, we also created a lot of jobs when we introduced industrial robots, because somebody needs to build the industrial robots. Whenever we introduce a new technology, we destroy some jobs, modify other jobs, and create new jobs. So robots have already completely transformed the way that we build things indoors. Why haven't they done the same thing for building things outdoors? Here's a picture from the building of the Empire State Building at the beginning of the last century. This is a picture from a construction site here on campus a couple years ago. Wouldn't it be great if we had robots that could help out on a construction site in the same way that we have robots that help out in a factory? Why don't we have them?
It's not the same repetitive movement every time.
It's not the same repetitive movement every time. So, yep.
And also there's different sites, so it'd be kind of hard to transfer such a large movable robot to smaller areas or different areas, because then you have to program it to do all these different things, and that would take time, which would be a waste of money when you can have people that can probably do it faster.
Absolutely. So every construction site is different, right? We might have to reprogram the robots for every new construction site, which would be very expensive and take a while. Maybe it just makes better sense to do things with people for the moment. Did you have an idea?
I was going to say weather,
right? So there's another thing that changes, right? What are all the things that could be different at different construction sites? Some might be larger, some might be smaller, might be raining, the environment is different. What else might be different from one construction site to the next? Could be up here, right? Exactly, not down on the ground. Imagine that we wanted to put robots in a construction site, and all they needed to do was clean up the construction site. They just needed to pick up bricks and put them over in pile B. The robots, and we say, you figure out how to do that. We put some AI in our robots and say, you figure out how to get all the bricks and put them in one pile. And the robot says, no problem, boss. Starts picking up bricks and throwing them 30 feet towards the pile that's over there. You did exactly what, the robot is doing exactly what we asked it to do. What's the problem? Safety, right? Maybe there are some of these things still moving around on the construction site. This is an GIV engineering, but we're going to do a little bit of philosophy for a moment. Over 2,000 years ago, the Greek philosopher Heraclitus said, man never enters the same river twice. What does that mean? What's that? Time moves in one direction, kind of. I don't think that was quite what Heraclitus was getting at.
everything is always changing and one river is never the same.
Everything is always changing, right? So I've given hundreds, maybe thousands of lectures about robotics by now, but never in this room. I don't think I've ever been in this room. I've never met you all before. You've never answered my questions in quite the same way that the GIV class did last year. So I do my best as we go along to adapt, right, and change how I talk about robots. You are all incredibly adaptive machines as well. When you came in this room, the organizers of the GIV did not have to say, okay, bend your knees to 40 degrees and gradually put your weight back so that you land in the seat. Please, you sit there, you sit there, you sit there. They just said, come in and sit down, right? And you figured out all the details, right? We are all very adaptive machines. It seems ridiculous, right? It's so easy for us. it is extremely difficult to build a machine that is adaptive. We can build complex machines like industrial robots, like this thing. We've built the International Space Station. We can build complex machines. What we don't yet know how to do, and that's why there's no robot that shovels the snow for you in the winter, we don't know how to build adaptive machines. So here at UVM in my group, that's the main question we're trying to answer. How do we build autonomous machines, machines that can decide on their own what to do, but also be adaptive? They can change how they do it as the environment around them changes. Okay, so how do we do that? How do we build autonomous and adaptive machines? Well, we know of someone who has been building adaptive machines for billions of years, and she's produced trillions and trillions of adaptive machines. Who is she? Mother Nature, right? Or Darwinian evolution. So I am not just a roboticist, I'm what's known as an evolutionary roboticist. So instead of picking up a screwdriver and trying to build a robot by hand, what I and my students do is we take one step back away from the robots. We write computer programs that evolve robots for us. And I'm going to show you one of these evolutionary simulations now. Okay. Here we go. You're looking at the results from a computer simulation. And the computer is showing you one robot after another. These are soft robots. They don't look very much like Big Dog. The little graph that you can see down here is the computer telling us this is the best solution I've found so far. And the computer is trying and evolving new robots, and suddenly it finds this one, moves a little bit faster, a little bit more. So what you're seeing along the horizontal axis here, this is evolutionary time. At any point in time here, there are hundreds of these robots, and the computer is showing you the best one out of all of those. They're kind of cute, right? If you're a coder, there's a URL at the top. You can actually download this code and try and evolve your own soft robots. And there's the best one the computer found after 1,000 generations of evolution had progressed, which took about 8 hours on the NASA supercomputer, which is called Pleiades. It exists down in Silicon Valley in California. Okay, so that's evolutionary robotics. You just saw how this works. I'll start it up again and tell you a little bit more of the details here. Okay, as I mentioned, we have a computer program. Inside that computer program is a virtual world, and that virtual world contains several hundred of these robots. Each one of the robots in this population has a slightly different... Oh, sorry, I can't pause it. I'll just leave it there. Oops. Okay, let's see if I can pause it here. Okay. Each one of these robots has its own unique body and its own unique brain. Let's talk about the body first. You can see these robots are made up of these small cubes. These are called voxels. So they're 3D pixels, or volumetric pixels, gives you voxels. The color tells us something about the strength of that voxel. So the red voxels are like muscle. They contract and then expand. The green is also muscle, but it expands whenever the red contracts, and vice versa. Think about your bicep and your tricep. When you're trying to pull your hand towards yourself, your bicep flexes and your tricep relaxes. When you want to move your hand away from you, your tricep compresses and your bicep relaxes. So you got these red and green muscles that are working in opposition. The light blue, this is soft passive tissue. This is like fat. It's basically just there, and it sort of wobbles and is pushed and pulled by the muscle. And if you look carefully in some of these robots, you might see a little bit of dark blue material. That is hard tissue or bone. So evolution is basically adding a little bit of muscle here, a little bit of bone there, a little bit of fat here, makes the body. Then it basically stitches inside this robot a brain, and that brain is made up of neurons and synapses that cause the robot to move. And so we now have bodies and brains for our several hundred robots, and the computer simulates each one among that population of several hundred, And some of the robots happen to travel a little bit faster than others, and some are a little bit slower. What do you think happens to the slower robots? Right? Mother Nature is tough sometimes, right? The computer deletes the slower ones, and we have a few fast-moving survivors. The computer picks these survivors, makes a copy of them, and when it's copying one of the survivors, the computer makes a random mistake. Maybe it puts muscle where bone used to be, or vice versa. Why would we ever program a computer to make a mistake? It seems odd. That's how evolution works, right? So we're simulating, we're putting in one of the important recipes of evolution, which is mutation. Sometimes we take two robots, cut them in half, take the two halves, stick them together to make a new robot. What are we simulating in this case? Reproduction, right? Recombination. We're trying to combine the best parts of two parents to produce a child that's better than either parent. That's the idea of evolutionary robotics. Okay, now that we have that, what exactly can we do with evolutionary robotics? Well, we can do lots of things. Here's another example. Here's a different sort of way of viewing this process. Here you can actually see all 16 robots at once. At this point in the evolutionary process, all of these robots are basically like cousins of each other. They're very, very genetically similar, which means they act very similarly. If we let this run for long enough, we're going to see that they're not exactly identical. They have very slight genetic differences that are going to cause them to start to move slightly differently, which is going to cause some of them to move slightly faster than others. And remember that we delete the slower ones, or our computer program deletes the slower one and makes randomly modified copies of the one that's moving a little faster. Which ones are going to survive and which are going to die? The ones that are involved in the traffic jam here, right? They're probably not going to make it. You'll see those two at the top of the screen and these two over here. These two look like they're probably going to survive into the next generation. Okay, so most of what we do in my lab is sort of computer science. It's a lot of coding. Where does the engineering come in? Well, when we've eventually evolved a robot that we think moves sufficiently fast or sufficiently interesting, then we go ahead and 3D print that robot, or parts of that robot, and get something like this. One of my students nicknamed this robot the evil starfish, and we'll come back and talk about the evil starfish in a moment. So we evolve robots in simulation, and then we 3D print them in reality and see how well they do. And hopefully, if artificial evolution works like biological evolution, it will give us not just an autonomous machine, but also a machine that can also adapt. Okay, let's see how that might work. Actually, before we look at that, let's pause here for a moment. What's actually going on inside these robots? I'm going to show you these different robots. These are known as Braitenberg Vehicles. They're named after a biologist whose name was Valentino Braitenberg. Braitenberg wrote a book called Vehicles. It's only about 80 pages, and it's a series of fairy tales about robots. It's a really interesting read if you're interested in robots. In that book, in chapter 2, Braitenberg says, imagine that there is this particular vehicle here called 2A. This robot has two light sensors, one on the front left, one on the front right. It's got two wheels on the back left and back right. Let's take a wire and connect the left sensor to the left wheel and a second wire to connect the right sensor to the right wheel. If we then turn on a flashlight and we come at vehicle 2A from its front right, it turns away. Why does it turn away?
Because the light sensor that's closer to the light is driving the wheel.
This light sensor is closer to the light than this one, right? Which means
drives that wheel faster.
Exactly. So this sensor is firing more strongly than this sensor, which means this wheel is going to turn faster than this wheel, which causes the vehicle to turn away from the light. What happens if it turns away from the light and we now chase the robot from behind with the flashlight? It runs away. So in his book, Vehicles, Braitenberg said, this is the coward. This robot is frightened to death of light. Seems kind of an odd thing for a biologist to say, but okay. Let's have a look at vehicle 2B, which is exactly the same as 2A. 2 light sensors, 2 wheels, but now we take the wires and we cross them. This one now, if the flashlight is in front and to the left of the robot, it will turn towards the light. Why? That's it, right? So this light sensor is firing more strongly than this light sensor, so this wheel turns more quickly and it starts to turn towards the light. What happens when it lines up and now it's facing the light? Goes straight at what speed? It'll get faster the closer it gets to the light. The closer it gets to the light, the more light that falls on the sensors, the faster the wheels turn, the faster the robot goes, and if it's a naked bulb, it will smash into it and break the bulb. This Braitenberg referred to as the aggressor. It hates light with a passion and will try and destroy any light source that it can get to. Seems kind of strange. This is a very serious scientist saying that this robot is afraid of light and this robot hates light. Does this robot actually fear? Does the other one hate? Seems ridiculous, right? Where's the fear circuit or the hate circuit in here? Humans, we have emotions, right? Sometimes you fear, sometimes you love, sometimes you hate. We are different from Braitenberg vehicles, right? Obviously. Why? Why are you different from a Braitenberg vehicle? You have a brain, so does this thing. Its brain has 2 wires inside. It's got a brain like you, so that doesn't work.
Because we've had millions upon millions of years of evolution and robots have not.
That's true. So maybe we throw millions of years and we get some more wires in there.
Because we don't think exactly in one way from our lives.
We don't think in one way, right? So this robot will always run away from the light. It'll never decide to do something else. In chapter 4, if you go back and read his book, he'll show you a robot that also changes its mind. It decides to do something else.
We can learn.
We can learn. That's true. These robots can't learn. Although you can put some machine learning or AI inside so that the strength of these wires, you'll notice there's little pluses next to them, can become minus or plus depending on what the robot is trying to do. So these robots also can learn. We have a lot more wires. This robot has 2 wires. In the human brain, there are synapses, these connections between neurons. You have 10 to the 14 synapses, as well as we can figure out. That's a lot more wires. Is that the only thing separating you from a Braitenberg vehicle? You have more wires?
We're alive.
We're alive. Aha, okay. Now, how are we going to define that? We're gonna pause this discussion here. Part of the reason that Valentino Braitenberg wrote this book is about what he calls anthro-chauvinism. You know what chauvinism is, right? It means that whatever group I belong to is better than all these other groups. I'm chauvinist. My group's better than all the other groups. What's anthro? Human, right? We're humans. We're better than animals. We're better than Braitenberg vehicles. We're special somehow. We're alive. We've got lots of wires. We can choose to do something else. What is it really that separates us from animals or robots? Ah, right, we're conscious, right? These things are not conscious. What is consciousness? You can kind of feel it, but it's not something we can measure very easily or figure out. Awareness, right, which is sort of a sister of consciousness. Consciousness is a sense of time. You can sort of sense time passing. Okay. Empathy, right? So you can feel sorry for someone or something else. We have memory, okay? Computers definitely have memory, which means robots could also have memory. We have morals, okay? Could a machine ever be moral? We could probably spend the next 3 days talking about this, but this is one of the fun things about doing robotics. It's not just engineering, it's not just computer science, it's also philosophy, theory of mind, and so on. It tells us something about human nature. If you think you really are better or different from animals or robots, building intelligent machines starts to challenge our notions of what it actually means to be different. I'll leave that there for some food for thought. Okay, let's come back to the engineering side. Let's look at some more practical robots. I mentioned that one of the nice things about evolutionary robotics is that we can make adaptive machines. So I'm going to show you an adaptive machine now. This is the Evol starfish. This is the birth of the starfish. At this point, this robot knows nothing about its world or itself. So what does it do? It just starts to move at random. If we were to peek inside the code that's running on board this robot, you would see this. This is how the robot currently thinks it's put together. It's clearly wrong. The robot doesn't have a good understanding of itself, but it has a little bit of experience that it's just extracted from the real world. It's going to take that experience and tune up, quote unquote, its understanding of self. Here it's evolving a sense of self, and you'll see right at the end of this video, it realizes that the best explanation of itself is that it has 4 legs, one in front, one to the left, one to the right, and one behind it. How did it come up with this understanding of self? It did it in the following way. The physical robot rotated motors 2 and 7, and by rotating motors 2 and 7, it tilted 10 degrees forward, and the robot can sense that tilt. It knows if I rotate motors 2 and 7 down, I tilt 10 degrees forward. The robot doesn't really know yet where motors 2 and 7 are, but where should motors 2 and 7 be on the robot that when they're rotated down, the robot tilts 10 degrees forward? On the arms, but where should they be? If I think that motors 2 and 7 are in front, and I rotate motors 2 and 7 down, what happens to me? I tilt back. So that's wrong. They're behind me, right? They must be behind me. So that's what the robot is doing. It's saying, when I move in this way, I expect that I should tilt 10 degrees forward. And by playing this game back and forth really quickly, the robot eventually converges on that explanation, then that explanation, right? It figures out where all its pieces are put together. The robot says, okay, I know this is what I look like now. And this was a project that was funded by NASA. NASA was interested in prototyping the next probes that they want to send to the outer moons of the solar system. So we built this for them, and we pretended in this experiment that NASA had given the robot a mission of moving from here to here. Pretty simple mission. So before the physical robot actually moves, it evolves a brain. So it's going to try out a whole bunch of brains, and it's looking for a brain that will get it from the left side of the video here to the right side of the video. In the same way that we saw a video a couple minutes ago where we had those soft robots that were evolving to go faster and faster, that's exactly what our physical robot is doing. It's evolving ideas in its mind, comes up with this way of moving, and comes up with this. So our robot has, on its own, figured out how to move. We haven't programmed it how to move, which is great. But this is only step 1 of a bigger process. As I mentioned, this was work that was funded by NASA. Why is NASA interested in adaptive machines? What happens if NASA spends billions of dollars building a new robot probe? They send it to Titan. It takes, I don't know, between 3 and 7 years to get there. The robot is coming in for a landing on Titan, and because of some slight miscalculation or maybe some wind or something else goes on, the robot comes in a little bit too hot, hits the surface, and bang, one of the legs breaks off. We've just lost 7 years of effort and billions of taxpayer dollars getting ready for this mission. You can imagine that NASA would like to try and get this robot to adapt even though it's been hurt and carry on with whatever it's supposed to be doing on the surface of Titan. So now we have a damaged robot, and according to this robot, it hasn't realized what's happened yet. This robot has no camera. It can't see its own leg. It doesn't know that it's missing. Our robot doesn't have any pain sensors. It can't feel that something's missing at the end of this leg. All our robot currently knows, I'm a quadruped. I have 4 legs, one in front, one to the left, one to the right, and one behind me. But now, when it rotates, oops, what did I do here? Oh, let me start this up again. When you make a presentation with a lot of videos in it, sometimes your computer cannot handle it. Okay. Okay. So our robot thinks that it's this intact robot, but it's suffered this damage. So now when it moves, it realizes before, when I was undamaged, I would tilt 30 degrees to the left, but now I only tilt 20 degrees to the left. Something has changed. So our robot pauses in its mission and goes back to trying to update its sense of self. Somebody mentioned that awareness is one of the things that separates humans from Braitenberg vehicles. This robot is self-aware in a primitive way. It's aware of its body, and it thinks up this idea, which is actually correct. It loses it for a little while, comes up with the idea that its leg has shrunk, but that doesn't make physical sense, so it throws that idea away, and right at the end of this video, it returns to the correct diagnosis, which is that its right lower leg is now missing. So the robot has sort of self-diagnosed its own problem. It says, don't worry, NASA, I realize I've lost part of my leg, but I'm good to go. I now have 3.5 legs. I'm going to carry on. So it goes back to thinking about how to fulfill NASA's mission. The mission is still move from the left side of the table to the right side of the table. The way it did it before worked when it had 4 legs, but when it has 3.5 legs, that idea doesn't work anymore. Remember that the physical robot is evolving a bunch of ideas. Now that that idea doesn't work anymore, evolution throws it away, and new ideas start to evolve and take its place. And the robot comes up or evolves this idea, this way of moving. Okay. And it tries it out in reality, and at least in this case, it's able to carry on with its mission a little bit. It's not perfect, right? Not the most efficient way of moving. It's not going to win any Dancing with the Stars competitions anytime soon, right? But gets there. Okay, tell me about the way this robot moved. What was good about it? What was not so good about it?
It moved in a way that was like it was getting, you had like limited motor capability. It was getting somewhere, it's sliding around, but
Yep.
it wasn't the most efficient if you want to go a very specific direction. It's just a flat terrain too. There could be bumps
And if there was a bump in the road, maybe this way of moving wouldn't work anymore. It's kind of sliding a lot. It also turns so that when it finishes moving, it's facing backwards, right? All we did was ask the robot to move forward. We didn't say which direction it needs to face in, right? Okay, so anyways, this was a start for this idea of building autonomous and adaptive machines. We can get a robot to fulfill NASA's mission when it's intact, and if it breaks or something goes wrong, it can still carry on. So this is a demonstration that with this evolutionary approach, we can start to make autonomous and adaptive machines. We have 10 minutes left, so let's finish with another project. I mentioned we were going to talk a little bit about language today, so let's finish with that. This is some new work we've been doing. If we want to build intelligent machines, we would like those machines to be able to communicate with us, right? We would like our construction site robot to say to us, I'm thinking about picking up bricks and throwing it to pile B over there. What do you guys think, right? If it can't communicate, all it can do is act. We probably don't have a very safe robot on our hands. How do we get robots to communicate with us? Here's an example of that. Here's yet another evolutionary simulation. Now we have this robot arm, and it is moving around, and you can see we place this object in front of us, and what you're watching is the beginning of the evolutionary process when there's a whole bunch of random robots. After a couple of hours of evolution, we start to get this. What do you think we asked the computer to evolve our robots to do? Pick them up, right? You can see we're starting to get there, right? Although the robot tends to fumble the ball quite a bit and can't seem to get it up off the ground. After 8 hours of evolution on the supercomputer, we got this. It is clearly managing to grasp and lift objects. This robot is also trying to communicate with you. It's trying to tell you something. There's no language yet. Our robot can't speak English, but it is communicating with you. What is it trying to tell you? You have to look very carefully at what objects it's actually manipulating.
It's putting certain objects to the left and certain objects to the right.
It's putting certain objects to the left and certain objects to the right. And which to the right? That's it. It's sorting, right? So what we've actually evolved this robot to do is grasp objects, lift them, and perform this thing up here, active categorical perception. It's a bit of a mouthful. So there's the categories. The categories are round and edged objects. How does the robot know which is which? Our robot doesn't have a camera, can't see the objects. All it can do is feel them. And based on what it feels, it should pick them up and tell us it's round by moving it to the left, or edged, moving it to the right. So the robot is signaling to us it knows about these different objects. If I were to take this object and put it in front of the robot and it picked it up and moved it to the right, what is the robot telling me about this object? The robot says, I think this is an edged object. It's not perfectly edged. There's some rounded edges. That's communication. The robot is starting to signal to us. But it's not language. We would like our robots to be able to speak English, to be able to talk to us. So I'm going to finish now with the last project, which is our attempt to teach robots some language. How do we do this? There's been lots of attempts since the 1980s to try and teach robots language. In the 1980s, they were downloading data sets into AI programs. Now people take all of Wikipedia and push it through a machine learning algorithm to try and teach it language. It doesn't work so well. Computers aren't very good at learning language that way. How else might machines learn language? Let's imagine that we have a robot. Our robot is moving over time. That's what the axis down here means. At this point in time, the robot is sort of keeping its feet on the ground, but at some point it moves in such a way that all of its feet come off the ground, and suddenly the robot senses zero pressure on the soles of its feet. At the moment that the robot suddenly senses that there's no longer any pressure on its feet, the robot hears humans say JUMP. Remember that our robots don't speak English, they don't speak any language. All they know is that whenever this happens to their sensors, they hear this. What does that mean? The robot might eventually learn that JUMP means this. So if the robot is moving and we were to ask the robot to jump, it would look at us and come off the ground. If the robot does that, we might say the robot now understands what the word jump means. It means come off the ground. Right? In essence, what we're doing is we're taking this word and we're grounding it in the robot's experience. It finds a relationship between these two things. Whenever this happens, it always hears from its human trainers this. Okay, let's stick with that for a moment. How are we going to actually do this? Well, we're going to do this with the robots using this. This is a project called Twitch Plays Robotics. Who knows what Twitch is? Can someone give us a 30-second summary of the Twitch website?
It's
There you go. So that's Twitch, Twitch Plays X, and Twitch Plays Pokemon. Twitch Plays Robotics. So Twitch, you can go there. People live stream video games. They live stream themselves cooking dinner, all sorts of crazy things. We live stream our evolving robots to the Twitch website. We then have another computer program which captures what people are saying as they watch our robots on the Twitch website. We tell people to think of our robot like a pet. This robot can learn certain commands, and there's lots of commands it probably can't learn, and we don't know which is which. So what does the crowd do on this website? Well, at the moment, this is a snapshot from the actual website. One person has said, let's try and teach the robot pet crawl forward. So they're voting for that. I'm going to see if I can... one other person has voted now for walk forward. They're voting for what command they want to try and teach the robot next. I'm going to speed this up a little bit. Now, down here, the robot is actually hearing WALK space, FORWARD. That's what it hears. Is this robot right now walking forward? No, not really. Two people just voted for no. Two people just told the robot, whatever it is you're doing, that is not WALK space FORWARD. Okay, what about this robot? Is it walking forward? Sort of, right? You can see no one's really voted yet for yes or no. One person said, no, this doesn't really count as walking forward. This website was running for weeks. We're now making version 2.0, so keep an eye out for Twitch Plays Robotics version 2.0. You can come and try it yourself. We got 5,000 commands that people tried to teach the robot. This is the internet, so you can imagine a lot of them were pretty bad words. One other command people tried to teach the robot was prove Fermat's last theorem. Probably not something that these robots are going to learn to do. But a lot of people said things like walk forward, walk backwards, walk left, walk right, and jump. After enough time, this robot and the four-legged one that you saw actually learned what jump meant. Whenever the crowd said JUMP, the robots would jump off the ground. So our robots had actually managed to ground this word in the soil of their experience. We got 2 minutes left, so I'm going to finish with this slide. How do we learn language? Most of what we do in robotics also ends up saying something about us, right? You're all pretty good English speakers. Where did our understanding of English come from? One theory is that, like the robots, we began to learn language by finding correlations between things like JUMP and our own experiences, things that you actually feel. Which seems weird, right? Language, math, these seem like abstract things that exist in here. They have nothing really to do with our body or our physical experience. George Lakoff is a linguist who studies language, and he says you can actually see evidence of the connection between language and our physical experience by looking at metaphors. A lot of the metaphors or idioms in English have action words in them, things that have to do with our actual experience. If you're in an argument with someone and they're trying to convince you of something, you might stop them and say, don't jump to conclusions. What does that idiom actually mean? If you tell someone, don't jump to conclusions, what does that mean? Assumptions. What does it have to do with the physical act of jumping? Seems kind of strange, right?
It's like you're skipping a step.
You're skipping a step, right? There's some chain in an argument your opponent is trying to make, and they have jumped to their conclusion, and you caught them doing it. Don't jump to conclusions. This is a very abstract idea, right? You're having an argument with someone about some logical chain of events, but you're actually grounding that idiom in this idea. If you have a friend from another country and they're not very good at English, try this idiom on them and ask them to tell you what it means. A lot of the times they can figure it out without you explaining it, because although we may all speak different languages, we all know what it feels like to jump and skip over a patch of ground or a bunch of chains in a bunch of pieces in a chain of our argument. Here's a couple more embodied metaphors. Don't look back in anger. What does that mean? What do you see if you look back, if you physically turn around and look behind you? I hear someone out there who had an idea. Don't look back in anger. Do you have an idea?
Basically just don't look at the past.
Aha, right? You're looking at the past. Why is looking back looking at the past?
Because the past happened before you.
All of your sensors tend to point forward, right? Your eyes point forward. So as you move around in your environment, your past is behind you, right? You're not literally looking back at the past in anger. You're metaphorically doing it. I'm looking forward to dinner tonight. Back tends to be associated with the past, forward with the future. Okay, let's end with some embodied metaphors of your own. What are some other ones that exist in English? Moving up the ladder, that's a good one, right? Up somehow has to do with advancement. What are some other embodied metaphors? Getting ahead of yourself, that's great. Jump the shark, that's a good one. I hadn't heard that one before, yes, perhaps. Okay, I think we'll pause there. We spent a lot of time talking about robots and lots of other things. I want to just leave this up here. We have a MOOC. If you want to program and evolve your own robots, come to Reddit and check out Ludobots. Enjoy the rest of the GIV. Thanks for your time.